Hello everyone, welcome back you all in this new video. Here we are going to see the professional approach for the manual design of the cantilever type of this slab. So this complete problem we are going to solve in a 5 important steps. In the first step we are going to see the problem statement, trial depth, effective span of the cantilever type of this slab. In the second step we are going to see the load calculation, maximum bending moments and calculation for the maximum shear force. In the third step we are going to see the design for the flexural reinforcement along the shorter and longer span of the proposed slab. In the fourth step, we are going to do the checks for the shear, deflection, cracks as well as for the development length. And in the fifth step, in respect of the design result, we are going to prepare the final schedule and details. And at the end of this video, I will give you bonus tips and tools to design the cantilever type of the slab in just less than of the 5 minutes. So it's request with you all guys, kindly watch this video till the end. Now, without wasting time, let's start the discussion. So here we are going to design the cantilever type of the slab. So for that, we first going to look at the problem statement. A part of structural floor plan is actually given here, and we have to design the cantilever slab panel as S6, which is present here, which is having the dimension as cantilever projection as of 2 meter and the width as of 5 meter. It is given in your structural floor plan. We have to consider the moderate environmental condition by considering the M25 grade of concrete and Fe415 grade of steel. The slab is subjected to a live load of 3 kN per meter square and the floor finish load as it is needed to consider as 1 kN per meter square. The size of the beam which is going to support this cantilever slab, so B5 is having 230 by 500 in mm. So these are the some given data for the designing of this cantilever type of the slab, which is as the name as 6. So let's start. First of all, we are going to write all the things which is given in your problem statement. So width of the supporting beam is 230 and depth is what, 500 in mm. Material property is M25 and Fe415 as given in the problem statement. Live load as 3 kN per meter square and the floor finish load as 1 kN per meter square. And later on we need to calculate the effective depth of the slab. So for calculating the effective depth of the slab, we need to assume the clear cover as well as we need to assume the diameter of the reinforcement. Later on, at the time of the design, this diameter may get changed. But for finding out the overall depth and effective depth at preliminary stage, we have to decide the preliminary diameter of the main reinforcement and shear reinforcement. So here clear cover we are going to consider for the slab as 20 mm. IS code has recommended that the minimum cover for the slab should not be less than of 15 mm. That's why we are going to consider the clear cover as 20 mm and the diameter of the reinforcement as 8 mm. So first of all, we are going to find out the trial depth and effective span of the cantilever slab. Actually, the loadings and everything is given. In respect of all this given data, we are going to find out the trial depth, and with that depth we are going to proceed for the further calculation, like we are going to find out the reinforcement and everything we are going to do for that trial depth. If that trial depth is going to satisfy all the checks, then we are going to finalize the depth of the slab. So for finding out the preliminary depth of the slab, we are going to refer the IS 456-2000 clause number 23.2.1 page number 37. That is the criteria for the deflection serviceability for the beam and slab element. So I would like to show you in IS code. So in IS code here it is present. So for the basic value of the span to effective depth ratio, whatever the span to effective depth ratio, based on the different type of slab is going to be changed, that ratio. So for the cantilever it is 7, for the simply supported it is 20, for the continuous it is 26. So for the proposed type of the slab, which is actually the cantilever type of the slab, we are going to take the ratio as span to effective depth. So cantilever projection is how much? 1200, 1.2 meter. As you can see, the cantilever projection is what? Sorry, by mistake here it is written as 2, but in actual it is not 2. It is actually what? 1.2 meter. We have to correct it. Okay. So here 1.2 divided by this 7, because effective depth we have to calculate, so that will come on this side and this 7 will come in the denominator. So 7. Now the new term here it is going to introduce as MF. So what does mean by this MF? So this called as modification factor. Very interesting and very important. What does mean by this modification factor and why it is needed to introduce here? So actually when you are going to deal with either the slab element or beam element, So it is subjected to the transverse load. If I am going to consider the beam or slab, doesn't matter. Both are the flexural element, both are subjected to the transverse load. So this is the longitudinal span or axis of the slab. This slab is going to be subjected to the load in this direction, that may be uniformly distributed or point load. Okay, so due to action of this load, your slab is going to deflect like this. So to resist this load before of deflection, only the concrete will not be present there. There will be presence of the reinforcement also, and that reinforcement also taking a part of resisting this load. Because RCC is a composite material, RCC is including the concrete as well as steel both, right? So concrete is going to resist this load prior to deflection, as well as whatever the reinforcements are present, that also going to take a part of resisting this load. But in the code, this span to effective depth ratio as given, it is 7 by considering only the concrete, not there is a consideration of the reinforcement which is present, and that reinforcement is also taking a part of resisting the load. So for that reason we are going to introduce this modification factor. And how you can calculate this modification factor? So proper chart is given, that we will discuss in detail how to calculate the modification factor when we are going to do the deflection check. So right now I'm not going to discuss that, but later on I will show you how to calculate this modification factor. So at the initial stage, because see, for calculating this modification factor, we need to have the percentage of reinforcement, and based on the percentage of reinforcement only you can calculate this modification factor. But at this stage we don't know how much the percentage of reinforcements are present in the slab. That's why you cannot calculate this modification factor value. That's why at the initial stage you have to consider this modification factor from 1 to at 1.5. So it may be different value. When you are going to do the calculation on your own, you may consider it as 1.2, some of you may consider it as 1.25, some of you may consider it as 1.3, right? So it's your choice what value you are going to take. So here I am going to take the modification factor as 1.5. Now after putting this modification factor 1.5 and this is a shorter span 1200 divided by 7, so we are getting the value of 114.28 in mm. This is what effective depth required, trial effective depth. Now as we earlier have assumed, as clear cover as 20 and diameter of the bar as 8 mm. So to find out the overall depth, your effective depth plus clear cover plus your half of your diameter of bar. Okay, here the 10 mm diameter of bar is what considered. That's why okay I have to correct it, as I'm going to consider it as 8 mm. So after doing this calculation, what value I will get, let me calculate that whether it is right or wrong. So it is 138.28. Now but 138 overall depth obviously we will not provide. We are going to round up this value by 150 mm. So overall depth of the slab we are going to provide here as 150 mm. Now available effective depth finally, so 150 minus 20. Now at this time here it is right value present. Earlier, okay, I have to correct this also. We are considering the 8 mm diameter of bar, not the 10. So after doing this calculation, what effective depth available? 150 minus 20 minus 4. So yeah, 126 mm. There is a presence of 126 effective depth. So we will do the further calculation with this trial effective depth. It is not the final one. If it is satisfying all the design checks, then we are going to keep it. Otherwise we need to decrease it, we need to increase it, we will decide it later. Next, as per IS 456-2000 clause number 22.2 C, if you are going to see this clause of IS 456, so it is recommended how to calculate the effective span of the cantilever type of the slab. So for calculating the effective span of the cantilever type of the slab, you need to add two values. One is your clear span plus half of your effective depth. So clear span is 1.2, means 1200 mm, plus 126 divided by 2. So finally we are getting the effective span of the slab in meter 1.263. That is what in meter effective span. So later on we will use this effective depth as 126 and we will use this effective span as 1.263. Hope that you all understood how to calculate the trial depth, effective depth of the slab as well as effective span of the cantilever type of the slab. Now look at The next step where we are going to do the load calculation, maximum bending moment and maximum shear force. Okay, so self weight of the slab, how you can calculate the self weight of the slab? So very simple, unit weight of the concrete should be multiplied by overall depth of the slab. So we are going to provide the overall depth of the slab as 0.15 in meter, and 25 is the density of your RCC material concrete. So after doing this calculation, we are getting the value of 3.75 kilonewton per meter square. This is what the weight of the only the slab. Now this slab will be provided with the floor finish. Floor finish will include what? Like if suppose you are going to cast the slab, so only the slab will not be the finished product. Obviously you might have seen the construction. After casting of the slab, we are going to put the flooring materials will be there as the sand, plus over of that we are going to put the flooring tiles, granite, marbles we are going to put there. So this bedding material plus flooring tiles combinedly called as floor finish. So that floor finish value is actually given as 1 kilonewton per meter square. Okay, so this is the purely dead load of the slab. This is the dead load we are going to apply over the slab as a floor finish. Now next, lie load, which is also given as 3 kilonewton per meter square. This is what the lie load. So total service load is going to become what? 3.75 1 plus 3. So obviously it is going to become as 7.75 kilonewton per meter square. So it is a service load combination. You know very well, when we are going to design the element, we are using the factored load, not the service load. So total factor load, whatever the load we are getting by service, we are going to multiply it by 1.5 to have the factor value. So it is going to become 11.625 kilonewton per meter square. So this is the factored value. Okay, now for this loading, total load per meter square, suppose this is what the slab. So for the 1 meter of the slab, how much the load is there? 11.625. This is the total load as a factor. Now I want to know the moment, as it is the cantilever slab. So you know very well, for the cantilever slab, maximum moment going to be acting at the support. Maximum moment due to this deflection. Your slab is going to be deflect like this. Let me show you. Your slab is going to be deflect like this. So maximum moment is going to be developed at the face of the support. Okay, so for that reason what I am going to do here, so W means total factor load multiplied by effective span square divided by 2. If it is a simply supported, then it is going to become W L square divided by 8 for the case of simply supported. If you are going to find out the bending moment at the middle of the span, but for the cantilever slab you need to apply this formula to have the moment. So total load factored multiplied by effective span square divided by 2. So we are getting the value of the moment as 9.272 kilonewton meter. Likewise, if suppose you would like to calculate the maximum shear force, so the total load you have to multiply with the effective span. So finally we are getting 14.682 kilonewton. Now ultimate moment of resistance of the section is going to become what? 0.138 FCK BD square. This is what the application of the moment which is going to be developed. These are limiting capacity, mu limiting. Maximum capacity of the section to resist the moment will be 0.138 FCK BD square. So from this formula we are going to find out the effective depth. So effective depth required, we already have provided the effective depth. Now I want to see, to resist this much moment which is going to be developed, how much the effective depth is required. So 9.272 into 10 raised to 6 divided by 0.138 25, and per width of the suppose this is the cantilever projection, that is 1.2 meter, and this is the width. So for a 1 meter width we are going to do the calculation. So it is going to become 51.84 in mm. This much the depth is required. So we have provided the effective depth available is 126 mm, which is greater than that of the required. Hence the provided depth is safe in the flexure. Flexure means what? Depth required for resisting the movement is only 51.84, but we have provided it as 126. So we are on safe side. Whatever the value is required, we have provided more than of that, right? So this is the thing, how to calculate the maximum bending moment, maximum shear force, then how to check your depth for the flexure. Now in step 3 we are going to see the reinforcement calculation for the both of the span. Basically we are having two span. If suppose you are going to see the slab, so this is a slab, this is a shorter span or the cantilever span, and this is the longer span. Okay, see, area of the reinforcement required along the shorter span, I can call it to the main reinforcement, because the cantilever projection is the main thing. Beam is actually present here. Okay, and the bars are coming here. So we have to anchor this bar in the beam. Okay, so that the stability of this slab we can ensure. This is the cantilever slab. So suppose the beam is present here. So the bar we are going to provide along this direction, shorter span, will be the main reinforcement, and the reinforcement you are going to provide in this longer span, this will be your distribution reinforcement. So it is, I can call it to cantilever one way type of the slab it is. Okay. So for that reason, 0.5 FCK divided by Fy, this formula are actually present here. You have to use this formula for calculating the area of the reinforcement required. So 0.5 multiplied by characteristic strength, grade of steel, then all the values 4.6, moment, maximum moment 9.272, everything you have to put here. Effective depth. After doing this calculation, we are getting the reinforcement demand 209.71 mm square, area of the reinforcement required along the shorter span, or I can say along the cantilever projection of the slab. Now, ST minimum, this is what the demand requirement to resist this much movement, 9.27. Now, what the code is suggesting to consider the minimum reinforcement? As per the codal recommendation, code is suggesting to consider 0.12% of the section size, that is B width considered overall depth. So this calculation is the minimum reinforcement. This will give the minimum reinforcement. So after doing this calculation, we are getting the minimum reinforcement to be provided as 180 mm square. So obviously, see, ST minimum is 180 and ST required is 209. So obviously, we will provide the maximum value in comparison of these two. If suppose minimum is coming out to be 300, then we will provide the 300. If suppose this value is coming out to be more, then we will provide more, as in this case. So 209 is more than of 180. That's why we are going to provide this value. Okay. Now next. However, the cantilever slabs are prone to creep deflection, because there are more chances of the creep deflection for the cantilever type of the slab. For that reason, the code has suggested to consider the minimum reinforcement that is recommended for the beam. If you are going to see the clause number 26.5.1.1 of IS 456-2000, there you will find the ST minimum as 0.85 B into D divided by Fy. But you may say that, sir, this clause is for the beam minimum reinforcement. So actually, we are going to check it with the beam minimum reinforcement. If this value is coming more, then we are going to provide this reinforcement. Why? It is because it is the cantilever type of the slab, and cantilever type of the slab will have in more danger. So that's why we are going to take the safety. And another reason is what? This cantilever type of the slabs are prone to creep deflection. That's why we are going to check with this minimum reinforcement. Otherwise, if you are going to design two-way slab or one-way simply supported slab, one-way continuous type of slab, any type of the slab is suppose you are going to design, so actually this will not be needed to do. Only this demand as well as this minimum reinforcement will be enough. But for the case of only cantilever type of the slab, you have to perform this check also. You have to take the importance of this minimum reinforcement as suggested for the beam. Okay, so yeah, 0.85 B into D divided by Fy. So after doing this calculation, we are getting 258. Now you have to compare this reinforcement, and this reinforcement. All these three reinforcements you have to check and see, and finally you have to decide the maximum amongst all these three. So I'm going to see this one, and this one. Now finally I am getting what? This 258.072 is the maximum one. That's why I'm going to follow this. After all of this, what next? As we have decided to provide the 8 mm diameter of bar, that's why 50.26 mm square unit area. This is the unit area of 8 mm diameter of bar. What is the formula? Formula is 5 by 4 D square. So that I am going to put here. So we are getting the unit area of 8 mm diameter as 50.26. So divide by unit area, divide by total area, as we have decided 258 over a 1 meter width. Over means, try to understand, very interesting and important for the detailing purpose. The reinforcement we are going to provide along the shorter span.
along the cantilever span. But for this cantilever span, the width is what? This one. So we are not going to do the design for entire span as 5 meter, because the digits will be more only. That's why we are going to do the calculation by considering 1 meter width only. So whatever the result we are getting for 1 meter, we will implement it to for rest of all the width. Try to understand. Okay. So for a 1 meter span, so it is going to become 194. So we cannot provide 194. And see, always you have to round down this value by the 25 mm to make it easy to execute on site, because 25 mm will actually be 1 inch. So on site it will be easy to execute. Either you can take 200, that is going to become what? It is going to become 8 inches. Okay, 194. So you cannot provide 200 because it will be greater. So reinforcement will be less. Suppose I am going to take the span, and demand is what? Spacing demand is 194, and I am going to provide 200. So if you are going to increase the spacing, the number of bars will what? Come outside of this section. So reinforcement will be less. So always you have to round down this value by 25 mm. So next to a lower value from this 194 will become 175. Okay. Now next 8 mm diameter of bar at a spacing of 175 mm center to center we are going to provide along the shorter span. Now next to this we have to calculate area of the reinforcement finally provided. As we have reduced the spacing, so definitely provided area of the reinforcement will increase. So that's why you can calculate the provided area by taking the ratio of unit area of the bar divided by provided spacing multiplied by for 1 meter width. Okay, so after doing this calculation we are getting the value of 287.2 mm square. So this much area of the reinforcement is finally provided. As per the demand it was 258. Due to reducing the spacing, reinforcement will obviously increase. That's why 287.2 mm square we are going to provide. Now for this provided reinforcement, in respect of this section, I am going to calculate how much the percentage. I want to calculate this reinforcement by percentage. So total area divided by width multiplied by effective depth. Remember, here you have to take the effective depth, not the overall depth, right? So after doing this calculation, we are getting the value of provided percentage of reinforcement as 0.2279. So this much percentage of reinforcement is available for a 1 meter span, right? Then same calculation we have to do for the longer span. We have done the calculation till now for the shorter span. Now I'm going to do the calculation for the longer span, and that reinforcement is called as distribution reinforcement. So for the case of the distribution reinforcement along the longer span, no need to do the calculation for the moment. Directly we are going to provide the minimum reinforcement. And what minimum reinforcement is? 0.12 divided by 100 multiplied by overall section size 1000 multiplied by 150. So 180 mm area of the reinforcement is required to provide as minimum. Now again unit area 50.26. If suppose you are going to provide 8 mm diameter of bar, so for the shorter span as well as longer span we are going to provide the same reinforcement dia. Okay, so unit area divided by total area multiplied by over the considered width, that is 1 meter. So maximum spacing required to provide as 279.22. So we had to reduce this spacing to lower. We are going to round down this value by 25. So that's why lower value will become 250 mm center to center. So 8 mm diameter of bar at a spacing of 250 mm center to center. Okay, finally area of the reinforcement provided finally. So that I need to put here by mistake, that is written as spacing. It should not be spacing, actually it should be the area. So we are going to correct it. Okay, ST of the reinforcement finally provided unit area divided by finally provided spacing multiplied by over the considered span 1 meter width. So total area is provided 201.04. Demand was 180. We are going to provide 201. Now what percentage is there? So 201 divided by 1000 multiplied by 126 multiplied by 100. So by percentage we are getting the value of reinforcement along the longer span as 0.1595. So it is greater than 0.12%, which is recommended as a minimum reinforcement. So it is greater than 0.12. That's okay, good. You have to provide a more than of 0.12 or at least 0.12. So we have provided as 0.1595 percentage, right? And the IS code has recommended to provide the spacing not more than of 5 times D. 5 times D, that is what? 5 times effective depth. How much the effective depth? We are having 126. So by mistake here it is written as 125, it is 126. So it is going to become 630, or in no any case IS code is allowing to provide the spacing more than of 300. So your provided spacing as 250 is less than of these two values. So that's a good thing. In no any case you are allowed to provide the spacing more than of these two values. Okay. So by this way, in this way, we have decided to provide the reinforcement along the shorter span as well as along the longer span. So along the shorter span, 8 mm diameter of bar at a spacing of 175 mm center to center, and along the longer span, same diameter of bar but at a spacing of 250 mm center to center. Right? Now, finally, the design has been done, but the checks are remaining. We have to check whether the provided depth is safe in deflection or not. Your design is safe in cracks or not. It is needed to design for the cracks or not. Whether the development length available will be enough or not. Whether the design is safe in shear or not, or it is needed to provide the shear reinforcement. That all comes under the checks. Okay, so in step 4 we are going to perform the checks. So very first we are going to perform the shear check. So nominal shear check. So suppose if we are going to consider the slab, so this slab is going to be subjected to the loading, transverse load. Due to this transverse load, the shear is going to be developed along the span, along the shorter span of the slab. So like how much the nominal shears are going to be developed, so that you can calculate by having the shear force value divided by B into D. So shear force value, we earlier have calculated what the shear force value, let me show you. So maximum shear force we have calculated as 14.682 is the shear force value. Here it is present. So this value we have to use for calculating the nominal shear. Due to action of the loading, how much the shear stress are going to be developed. So this much shear force divided by width 1000 multiplied by effective depth. So nominal shear is coming out to be 0.117 due to action of loading. Now we have to check what is the capacity of this concrete to resist this shear. Again I am repeating, this is my concrete slab which is having the support here. Okay, and due to action of the loading, obviously maximum shear is going to be developed here at the support. So due to that there is a possibility of development of the cracks if the shear is more than of the capacity of the concrete. So due to action of the loading, whatever the loading is there over the slab, due to action of that loading and due to shear force, how much the nominal shear stress at this section near the support of the slab. So nominal shear is what? 0.117. This is what the action. Now what is the resisting capacity of your concrete? Tau C, shear resisting capacity, critical capacity of your concrete I want to calculate, right? So how I can calculate the shear resisting capacity of your concrete? So for that I need to have the percentage of reinforcement provided. So percentage of reinforcement provided along the shorter span is 0.2279. So that I am going to put here as 0.2279. Therefore, as per IS 456-2000 table number 19, so there you can find the critical capacity of shear resisting capacity of your concrete tau C will be what, based on your grade of concrete and based on your percentage. Okay, and in this percentage effective depth is there. Remember, most of the times while doing the design, many of the people are doing this mistake. They are considering the overall depth. No, here effective depth you have to consider. You can see in the code. Okay, very clearly it is given, it should be effective depth, right? So our percentage of reinforcement is how much? 0.2279. So this comes in between 0.15 and 0.25. So for 0.15 and for the grade of concrete 0.25, it is 0.29 and 0.36. So our value coming in between this. So I have to calculate critical capacity for this value. So we need to do the linear interpolation. Okay, 0.15, 0.29, 0.25, 0.36. But we have to calculate the value for this. So that is what unknown. So after doing the linear interpolation, I am considering that you all know what does mean by the linear interpolation and how to do the linear interpolation. So after doing this calculation with linear interpolation, we are getting the value of tau c for this percentage of reinforcement as 0.3445. So this is the critical capacity of your concrete. Capacity, whatever the concrete is present, it is having the shear resisting capacity 0.3445 and your nominal shear is 0.117. So whatever the stress is coming, which is less than that of the capacity. So okay, no need to design for the shear as well as no need to provide the shear reinforcement. Your design is okay, your depth, your reinforcement, everything is okay for the shear check. Next, we have to do the deflection check, whether the provided depth is safe in deflection or not. But you can recall at the start of this problem, while we are going to calculate the preliminary effective depth, there I have discussed important point about the modification factor. What we have discussed, this modification factor, it is actually the factor of presence of the reinforcement. Like when the load is coming, so only concrete is not there for resisting this load against the deflection. There is also presence of the reinforcement. So reinforcement plus concrete both are going to take a part of resisting this load to control the deflection. So actually we have to calculate that modification factor, and that modification factor is actually the representing the contribution of reinforcement for resisting the deflection. So obviously we need to see the percentage of reinforcement available. So provided percentage of reinforcement is what along the shorter span 0.2279. Obviously your cantilever slab will deflect along the shorter span, not along the longer. It is going to be deflect along the shorter span. So in this way it is going to deflect. So I want to calculate this deflection whether it is in limit or not. Okay, so percentage of reinforcement available 0.2279. Now as per the code IS 456-2000, the formula has given how much the stress in steel. Let me show you in your code. In IS 456-2000 page number 38, this chart and graph is actually given for calculating the stress in your reinforcement in your steel. So that is the formula 0.58 Fy yield strength multiplied by area of the reinforcement required divided by area of reinforcement provided. So this is actually the stress which is going to be developed in your steel, because the load like when it is coming, so the stress will be developed in your concrete as well as in your steel. Then only both are going to resist the load. So how much the stress is going to be developed in your provided reinforcement, I want to calculate that. So for that reason, the formula is what 0.58 multiplied by Fy multiplied by area of the steel required divided by provided. So earlier we have seen the area of the reinforcement required while doing the calculation along the shorter span was how much? Area of the reinforcement minimum required as 258 and finally provided as 287. So that two value you need to put here. See 258, 287, right? So after doing this calculation, we are getting the how much stress is going to be developed in your reinforcement. So 216.29, this much stress is going to be developed in your steel. Now in your books you have to go through this chart for finding out the this modification factor. Okay, this modification factor due to percentage of reinforcement along this span and modification factor by intersecting the point, you have to find out the modification factor. But I am not going to adopt this practice. I am going to use this formula for calculating the modification factor. So KT, that will equal to 1 by 0.225 plus this 0.3322. These are constant values multiplied by stress in steel minus 0.625 log of 10 of inverse of percentage of reinforcement provided. If you are going to put all this value, so you are getting the modification factor as 1.9229. I am getting the title as KT. This is nothing but your modification factor for the tension reinforcement, 1.9229. Or otherwise you can go through the chart also. Let's try with the chart what value we are getting. So here 0.2279, so almost 0.23%. So go to your chart 0.23%, so it is 0.2, 0.4, half of that 0.2, 0.23, somewhere here. So I'm going to project this line over the y or over the height. Let me show you. Okay, what are the FS value? It is approximate. Exact value you will not get. Now what next? FS value. How much the FS value? FS value we have calculated 216. Where the 216 is available? 120, 145, 216. So in between of these. Okay. So I'm going to take this line 216. So curve for the 216 is not available. So we have to assume it somewhere in between 190 and 240. So yeah, somewhere here we can project it here. So 1.6, more than of 1.6 it will be. Yeah, it will be what, like this. So yeah, 1.8 something. So by the formula we got the value as 1.9. By the chart we are getting 1.8, or by actual formula we got the value as 1.922. So we are going to follow the value with this formula 1.9229. Now I am going to put this value. Now span to effective depth, actually 1200 divided by 126, 9.524, and permissible L by D ratio 7. Like span to effective depth ratio, IS code has recommended to consider for the cantilever slab as 7. Now we are going to multiply it with the modification factor. So we have calculated modification factor as 1.9229. So after doing this, we are calculating the permissible allowable L by D ratio is 13.46 and actual 9.524. So your actual value is less than of your permissible. So it's okay. Your slab satisfies the deflection criteria. In any of the case, if you are getting your actual value more than of this value, then you have to revise the design by increasing the depth of the slab. At that time, you can say that your depth is not sufficient to resist the deflection. Okay, but here in our problem, depth is satisfying the deflection criteria, right? So first criteria for the shear is what? Okay. Second criteria or second check for the deflection, that is also okay. Now third check we are going to perform as check for the cracks. So two spans are actually there. So we need to check whether the provided reinforcement and spacing and diameter of bars are okay or not. Then only we are going to decide whether the crack checks or crack analysis is needed to perform or not. So along the shorter span, as per clause 26.5.21 IS 456-2000, you can see this. Diameter of bar, if it is less than of overall depth divided by 8, that we can check. We have 8 mm diameter of bar which is less than of overall depth 150 divided by 8, so 18.875. So provided diameter is less than of this value, so it is okay. You are not allowed to provide the diameter of bar in any of type of the slab, not only in cantilever. In any type of the slab, diameter of provided bar should not be greater than of overall depth divided by 8. So obviously the limiting diameter is what? 18.75, and we have provided as 8 mm. That's okay, good. Second, as per the clause 26.3.3 of IS 456-2000, maximum spacing along the shorter span should not be more than of 3 times effective depth. So 3 times effective 126, it is mistakenly I have taken it as 125. It is going to become 378. So first, second, 300. Okay. So in no any case you are allowed to provide the spacing more than of these two values. So you know very well, along the shorter span we have provided 8 mm diameter of bar at a spacing of 175 mm center to center. So provided spacing is less than of all this allowable spacing. So that is a good thing. Diameter is also as per the limit. Okay. So if everything is okay, then no need to do the design for the cracks along the shorter span. That is what safe. Likewise, we have to do the calculation for the longer span. IS 45000 minimum percentage of reinforcement should be at least of 0.12%. IS code is recommended to provide 0.12% for the slab. So we have provided the reinforcement as 0.1595 percentage, which is more than a 0.12. Again the spacing criteria. So if you are providing spacing less, so you will get more reinforcement. So we have provided more reinforcement than that of the minimum one, so that's a good thing. Provided spacing for the distribution reinforcement, so that should be what? 5 times effective depth. So 5 times effective depth is going to become 126. how much it is going to become? 630. So your provided depth is 250. Allowable is what? That should not be more than of 5 times effective depth. So 630, it is less than of 630. That's good. And in no any case you are allowed to provide the spacing for the distribution reinforcement is 450, not 300. Okay, 450. So for 450, it is also less than of 250. So hence the spacing provided is 250, which is safe in respect of all these recommendation. That's why no need to design for the cracks along the longer direction also, along the shorter direction also. So this is actually the criteria. Now the next check for the anchorage, whether the sufficient span is available or not for the anchorage, because it is the cantilever slab. Try to understand, this is the cantilever slab. So if you are not giving proper length or the span of the reinforcement being as anchored in this concrete, so you cannot ensure the serviceability of this cantilever slab or life of this slab. That's why we have to anchor proper length, required length of the bar in this concrete. Remember, so for that reason, what to do? Just go and let's check whether the sufficient span is available or not. So as per SP16 table number 65, where it is present for the FY 415 grade of steel, and for M25 grade, and for 8 diameter of bar. So for all that criteria, see, for the tension reinforcement, for the 8 diameter of bar, and for M25 grade of concrete, what? 32.2 centimeter. So if you are going to calculate it is in mm, so it is going to become 322. So this much minimum anchorage length should be present. Sometimes we are calling it to development length also. Anchorage length or development length, both the things are same. So 322, it is needed to be provided at least. Okay, but we have to check whether that much space is available or not to anchor the bar. So we are going to provide 90-degree bend of the reinforcement, because the bar is coming from here. So we are going to provide the angle like this. So this is going to become 90-degree, right? So 90-degree is there. So for that reason, what? How much the span is available? So like see, it is what? It is 200. We are going to consider the side cover as 30 mm. So if you are going to subtract 230 minus 30, we are getting 200. So this 200 is available. Okay. Now next, plus we are going to take the leg of 150, because 500 depth is available. So we can take up to the 150. So 150 span. So 200 plus 150. This much anchorage is available. Okay. Plus in that, what to do? We have to add one more thing, that is what here it is given, due to anchorage, because it is a bar. So you know, when you are going to bend it like this, so this is 150 and this is 200, this is 200 and this is 150, but due to this bend, this extension will be there. We have to add this extension, and that will be equal to, like if it is 45 degree, it is 4 times. If it is what? 90 degree, if you are going to increase by 45 more, so it is going to become 8 times. It is, if you are going to increase more, it is going to become 4. So every time, for every 45 degree, you have to increase it by 2 times, right? So 4, 8, 12 and 16. For 45, it is 4 times diameter of bar. For 90 degree, 8 times diameter of bar. For 135 degree, 12 times diameter of bar. And for 180 degree, 16 times diameter of bar. So in our case of the detailing, we are going to provide it as 90. Okay. So 8 times diameter of considered bar. So I'm going to take 8 times diameter of considered bars. Diameter of bar is 8. So after doing this calculation, available span or available length for anchoring the bar is what? 414. And as per the codal recommendation, you should have the minimum anchorage space or anchorage running length at least 322. So it's a good thing we are having more space in comparison of demand. So we can extend the bar up to this what? 414, and we are anchoring the bars to a 414. So that is more than of the required, hence it is adequate. Proper anchorage length is what? Available. So there is no possibility of slip and failure due to this anchorage. Okay. So this is all about the design of your cantilever type of the slab. Now in respect of all these design results, we are going to prepare the schedule. So like it is the serial number first, and the slab label is what, S6. If you are going to see the given floor plan, so it is a floor plan, so that slab panel name is what, S6. Okay, and this is not 2 meter, remember it is 1.2 meter. Remember it is 1.2 meter. I will correct in PDF file that you can download. So in detailing what to do, we have this label, slab label as S6. Overall depth we have provided as 150, and reinforcement along the shorter span 8 at 175, reinforcement along longer span 8 at 250. It is the cantilever type of the slab. Now have a look over the detailing. So shorter span, effective span is what, 1.315. let me check effective span, it is right or not, I have a doubt. Now effective span is 1.263, so we have to correct it. 1.263 effective span, 1.263, this is the effective span. Now then along the width is a 5 meter overall span. Thereafter the reinforcement along the shorter span 8 at 175, and along the longer span 8 at 250 center to center, right? So in plan detailing of the reinforcement, sectional detailing of the reinforcement along the shorter span. Okay, we are going to take the section. Here is what the section. If you are going to see the reinforcement along this shorter span, so we are getting the detailing like this. So this is what, red one is your main reinforcement, 8 mm die at a spacing of 175 mm center to center, and blue one is your distribution reinforcement as 8 mm diameter at a spacing of 250 mm center to center. Now one important thing you can notice from here, that is what, we have decided to provide 150 mm depth of the slab at the support, but here towards the end gradually I am reducing the depth. Why? See, in calculation, I have not taken into account, but in detailing, you can reduce it. Why? Because we can save the concrete. Because maximum movement is going to be developed at this support. So, to resist this maximum movement, more depth are required only at the support. But at this end, there's no any movement. It is zero, free end. So, there's no need to provide that much depth. That's why we can reduce the depth gradually towards the end. So, I have decided to provide it as 100. You can take 125 also, or suppose if you are not willing to save the concrete, then you can take same depth as 150, your choice. So here intentionally what I have done, I have decided to reduce the depth over the span towards the free end. Now next is a section along the shorter span, 8 mm dia at 175, and 8 mm dia at 250 along the longer span, and the anchorage we have provided as 400 what, let me show you again, 414 mm is actually available. 200, then this extension due to curve, and then this leg as of 150. Okay, so this is all about how to complete the design of the cantilever slab. Hope you all understood the complete design calculation. Now it's a time to discuss some bonus tips and tools to design the same type of the cantilever slab in just less than of 5 minutes. Now this spreadsheet we are going to use for the designing of that cantilever slab, and this is a very advanced level Excel sheet which is capable of designing all types of the slab as one way, two way, cantilever, all the different types of the slab you can design by using this Excel sheet. So here you have to edit the values in the yellow cells only. In white cells you don't need to do anything because the values are going to be adjusted by the cell itself in the white cell. In this color cell it will suggest the value that will suit the design. In black cells you don't need to do anything, you have to skip that area, and if you are getting somewhere as red cell, so that is what the sign of the danger and failure. Okay, let's put all the given data. So in our problem statement we said that we have to use M25 grade of concrete, so you can choose the grade as per your convenience, as per your problem statement. So drop down list are there. Next, all the grades of steels are present here, you can choose your grade of steel. Then shorter span is 1.2, longer span is what, 5 meter. Now it is the type of one way slab, the sheet is going to decide by its own. If suppose I am going to choose it as 4, so obviously it is going to become two way slab. So you just have to put the dimension accordingly, your sheet is going to decide the type of the slab. So yeah, it is the one way slab. Now in case of one way slab, it may be of three types, either simply supported, continuous, or cantilever. So we are going to design the type of the slab as what, cantilever. That's why I'm choosing this cantilever. Now here the trial overall depth. So I am going to choose the trial overall depth to match with our manual calculation. So in our manual calculation we have considered the overall depth as 150. Now width of the supporting beam is 230, clear cover as 25, and side clear cover we have considered as 30. Now diameter of the main reinforcement we have considered as 8 mm. So if you can able to recall, so effective depth was 126. Sheet is also calculating the effective depth as 126. Again, if suppose you are able to recall, so effective span along the shorter direction was 1.263. So that is actually what sheet is also calculating. Effective span that is not needed, but the sheet has done 5.23 along the longer span. Now here aspect ratio, it is more than of 2. It is a one way type of the slab. Now these all parts are required for the two-way type of the slab. So you don't need to worry about this. Let it to be present as it is. You don't need to edit anything in the white cells. Okay. Now moving forward, we have to set the loading. So self load of the slab is going to become 3.75. Floor finish we have to adjust here as per the problem statement. In our problem statement, it is given that the floor finish is 1. Okay, so you have to put the values here, density of the floor finish and thickness of the floor finish, such that this output should be as per your requirement. So okay, I'm going to fix this density as 20. Now increase the thickness of the floor finish to 100. So it is going to become 2. If you are going to 75, so 1.5. Okay, so floor finish is going to be adjusted by these two cells. So I'm going to fix this value density. I'm going to change the thickness. So I'm going to take it as 50 only. So accordingly, it is going to become 1. Now lie load has said that to consider as 3. So finally, maximum moment 9.272. If you are capable to recall, so our maximum moment was 9.272. Okay. Now along the shorter span, 8 mm diameter of bar, 194. So we are going to provide 175 mm spacing. Accordingly, the percentage of reinforcement is going to become what? 0.228. Now, as you can see here, the percentage of reinforcement along the shorter direction 0.2279. So it is 0.228. You can call it 2. Now look at this sheet, and 175 mm spacing we have provided. So it is 175 spacing. Right. Now next, along the longer dimension, we are going to provide 8 mm diameter of bar. 279 demand is there. We are going to provide 250. If you are going to compare it with your manual calculation, so you can see here along the longer span, 250 mm center to center spacing we have provided reinforcement along the longer span. Right. So 250.1596, it is the percentage of reinforcement 0.1596. Okay. Rest of all checks are actually present here. Check for the flexure. Your provided depth is safe in the flexure. Your provided depth is safe in deflection. Your provided depth and design and reinforcements all are safe for the shear. No need to design for the shear, as well as all the checks are okay for the cracking also. We don't need to do the design for the cracking. Okay, so these all checks where is going to be performed. If any of the checks are going to be failed, so that will be intimated by the sheet by the red color. And finally, the schedule is actually present here. So this is a type panel name. I am going to say S6 panel. Overall depth is 150, automatically will be present, and reinforcement along the shorter span 8 at 175, along longer span 8 at 250, and one way slab it is. Here the schedule sheets are present. So if suppose you want to clear all that entries first, so you have to say clear all. So all the entries of this schedule is going to be clear. Now if you are going to click here as send to schedule, once you click over the send to schedule, this all data will be sent to final schedule sheet. Okay, so using this sheet you can design all the different types of the slabs as one way, two way, and cantilever type of the slab, and all the floor slabs. Okay, having the 9 types of the panels as suggested by your IS 456. So it is a very advanced tool for the designing of the different types of the slab. Hope you all understood the manual approach as well as how to design that same slab by using this tool. Thank you.
Welcome you all in ASO certified live training program ETABS, RCDC and Excel that makes you a professional structural engineer. In this training program you will learn everything about ETABS and RCDC from basic to advanced, real life project of medium rise structure from architecture plan to final design sheet, Real life project of high-rise structure with all advanced topics. Design of structural elements using advanced Excel sheets. Have a look over the features of this training. Daily live classes conducted by expert for 1.5 hours. Recording of every session with lifetime access. Can interact with expert anytime 24/7. Exposure to real practice. ISO certification of training completion. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next. Hello everyone, welcome you all in a new ISO certified live training program. Design of substructure using CSI Safe, Excel and manual. In this training program you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second we will cover all the types of isolated foundation in CSI Safe software. In the third real life project we will cover the raft foundation, and in the fourth real life project there will be the coverage of pile and pile cap design of basement wall, and at the end of this training program we will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by expert. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next.